So for limits, algebraically, what you want to try every single time is you want to try direct substitution. Because if you can plug in a number and it gives you a value, that is your limit. All right? So if we look at this first problem here, if I take 2 and plug it in for my x, 3 times 2 squared minus 4 is going to be 3 times 4 minus 4, which is 12 minus 4, which will give us 8. So that's my answer. All right, so if you can plug the number in, then the number you get when you plug in for x is your answer. So it's called direct substitution. It is the quickest and fastest way to solve a problem if it works for a problem. Number 2 is a little bit tricky. What is 2? What's the answer for 2? It is 5. Some students, what do you think students would say? What would they say is their answer if they got it wrong? What do you think would be a common way for them to get it wrong? 0. Because they, even though there's not an x there, they kind of like try to plug it in for an x, and they'll do 5 times 0 and get 0, but there's no x there. So if you have a constant number, just a number, your answer is that number. It doesn't matter if this is x approaches 0, x approaches 10, x approaches 4, x approaches infinity. It does not matter what it is. This is going to be 5 every time. Okay. All right, and then if we get something like number 3, we're going to have the square root of 6 plus negative 2, which will give us the square root of 4, which equals 2. So 2 is our answer. Okay, direct substitution. Easiest way to solve a problem. As you can guess, you're not going to see a ton of these problems because they're too easy, right? I wouldn't give you a page of these. A lot of times we're interested in graphs that have problems. These are all continuous graphs. They just are, 5 is just a horizontal line. 3x squared minus 4 is just a parabola that we have there. It's a continuous line. It's going to have a limit at every point. Square root of 6 plus x. Everywhere it's defined, it's going to be continuous. Now, you would have an interesting point at negative 6 right there where you would care about your limit there. So, or any negative numbers. So, most of the time you don't get questions quite this easy. But you got to watch out because they sprinkle them in. They will sprinkle these questions in amongst the difficult questions. And what I have found is a lot of times students miss these questions more than they miss the difficult questions because they forget that they're supposed to do this. So technically you're supposed to do this every single time with every problem. Try to plug the number in. If you get an answer, that is your answer. But you're going to see most of the time we're going to be concerned with ones where direct substitution fails. And it can fail in 2 different ways. So the first way that we're going to look at that direct substitution fails is that the limit does not exist at all at that point. Okay? And so that will look like a problem like this. The limit as x approaches 0 of 3 over x. So if I plug in 0, I get 3 over 0. Now, 3 over 0, what is 3 over 0? It is undefined. We cannot divide a number by 0. Okay? So since this is undefined, now, I'm saying that 3 over 0 is undefined. But what do I say about the limit? The limit here does not exist. Okay, so the number 3 over 0 is undefined when we try to do that, but the limit does not exist. Does not exist is your answer for this. So anytime you get some number over 0, that is going to be does not exist for the limit answer. Okay, I'm going to put limits here. technically number over 0 is undefined. There goes the interchangeability of those. They're not really interchangeable, but they seem like they should be interchangeable, right? So, now, except there is one case where we do not necessarily have does not exist. And that is when we get what we call the indeterminate form. So if we look at this problem right here, if I plug in 5, now I'm going to do something that is mathematically incorrect, and later I'm going to tell you that you cannot do. So I'm just warning you of that. In this whole unit, it's okay if you do what I'm getting ready to do. When we learn about L'Hopital's rule later, I'm going to tell you can't do this. Because on a technicality, it technically does not equal 0 over 0. So I would have 5 squared minus 4 times 5 minus 5 over 5 minus 5. And that gives us 25 minus 20 minus 5 over 0. And that gives us 0 over 0. Now, what I've done that's mathematically incorrect is I have said that this limit equals 0 over 0. That is really not true, because what this is called is the indeterminate form. And what it tells us is just like it sounds like. We cannot determine anything from this answer. We cannot say that the limit does not exist, but we also cannot say that it does exist. We just don't know. So when we get the indeterminate form, we're going to have to keep going. Hopefully there will be something that you can do to your equation that will allow you to see if there is in fact a limit there, or if it actually does not exist. Because you can't tell when you get 0 over 0. Now, if you get a number besides 0 over 0, then that is automatically does not exist. You don't do anything further. Now, when we get to L'Hopital's rule again, I'm going to tell you you can't say this equals 0 over 0. And we'll look at what we got to do differently. But for what we're doing right now, this is fine. You know, it technically can't equal that because the indeterminate form is not something that it can be equal to. If we ask Siri, hey Siri, what is 0 divided by 0?
If nothing is divided by nothing, then there's nothing to divide or divide it with, and the division never happened. So my answer is no.
Usually I've never tried it on my watch. Usually she talks about Cookie Monster having 0 cookies and giving them to his 0 friends, and Cookie Monster is sad because he has no cookies and no friends. But we can't divide 0 over 0, right? It is indeterminate form. So, when we get indeterminate form, there are several methods that we can use. So the first thing we're supposed to do every time is try direct substitution. And remember, I told you that this is what's going to get you sometimes. You're going to forget this step, and maybe you assume it's 0 over 0, and it's really not. So I don't mind if you do this part in your head. You don't have to write it down. I'm going to write it down just so we're really clear that we're checking that every time. So, negative 2 squared minus 3 times negative 2 minus 10 over negative 2 plus 2. That is going to give us 4 plus 6 minus 10 over 0, so we get 0 over 0. And again, that is called the indeterminate. It's not our answer. Maybe I shouldn't have put that box around it. Form. We need to keep going. Alright, so this is not my answer. I need to do something else. And so the first method we're going to look at is cancellation. If I have something that can factor, I want to factor and try to cancel. So, important thing about notation here, because this will matter, and on free response questions, it could cause you to lose points. Right here, I did not write the limit notation because I was plugging in that number. But until you plug in the number, -2, you have to keep limit notation. So you may be tempted to do this. You may be tempted to factor like so. And let's see, that'll factor -5, +2. And then just keep answering the question. But right here, I have not plugged in a number, so I have to do the limit as x approaches -2. You have to keep that notation right there. It is required that you still write that limit notation. Then I can cancel x plus 2 and x plus 2. So now what I'm dealing with is the limit as x approaches -2 of x minus 5. Notice I still have that limit notation because I have not plugged in the -2 yet. But once something cancels, you can plug in the value most of the time. So if I plug in -2 now, -2 minus 5 is going to give us -7. And what's happening here is we got a hole in the graph. If you remember back to pre-cal, when we had rational equations, I asked you to find holes and asymptotes. So if you have a factor that cancels, at that point you're going to have a hole in the graph. If it does not factor and it's from the denominator, you have an asymptote. There. Okay. Questions? All right, I need to teach you something new here because I don't think I've ever taught this to you. So, anybody know how to factor a cube, a perfect cube? Any of you ran into that in any of your other crazy classes? I'm pretty sure I've never shown you that in my classes. So, a cubed plus or minus b cubed. Here. If we factor it, it can be factored into a plus or minus b times a squared minus or plus ab plus b squared. This is the formula that we're going to use. You're not going to run into this a lot, but our textbook puts some problems in like this, so we're going to do one to practice. And this is called a factoring perfect cubes. All right, so notice the signs here. Here I've got plus or minus. I just did that because it could be a positive or it could be a minus. You're not going to see the plus or minus written, right? This sign matches this sign, but it's the opposite of this sign. That's why it's a minus or plus, right? So it matches your sign you have here. It's the opposite of the sign you have here. And then this right here is always positive. I'm pretty sure. I'm feeling a little nervous. I might not should trust myself. Let's just make sure. I have taught students how to do things incorrectly before. Yeah. Let's see. Yeah, I did it right. All right. Just to verify. So let's do an example of just factoring a perfect cube first. So this is just like a side example, and then we're going to do example number 5 that's given here. So let's say that we had a problem that said factor x cubed minus 27. Hold on. Yeah, that's right. Make sure 27 is perfect cube. Yes. All right. So X cubed is a perfect cube. If we took the cube root of it, we would just get X. 27 is also a perfect cube. What is the cube root of 27? 3. Right. So let's think of it this way. It's X cubed minus 3 cubed. Right? That's equivalent if we write it that way. So if we are going to factor this, if we use this formula, our A is our X here. Our B is our 3. So we would say X, we use the same sign, minus 3. That's our A minus B, right? And then we would have A squared, which in this case is X, so we'll have X squared. We switch our sign, so where this is a minus, this one's going to be a plus. What is A times B going to be for this problem? 3x, because our A is x, our B is 3, plus B squared. So I'm going to write it this way, 3 squared, because our B is 3 squared, but you could have went ahead and skipped to x squared plus 3x plus 9 there. That's something that used to be done in Algebra 2 a lot. I don't really think it's in the new curriculum. And if it is, it's never really tested in the new curriculum, so nobody ever really does it. But it shows up in our book every once in a while, so I just wanted to go over it. There's a chance I might give you a problem like that as well, so you might want to, you won't see lots of them. You might see one on a test, maybe. I can't remember, actually, if I put it on the test or not, but it seems like something I might would do. If I need to find this limit here, I want to factor. So this is a perfect cube right here because it's x cubed minus 1, and 1 is a perfect cube, right? I could think of that as being 1 cubed because that would still be 1. So if I'm factoring here, I'm going to keep my limit notation because I'm not plugging in yet. And so I would have x minus 1. And then it's a squared, so that's x squared, minus a times b, so 1 times x, so that's just going to give us x. Oh wait, what have I done wrong? That should be a plus for that second one right there. Those two signs should never match, right? It's going to be the same sign as your original here, different sign here, then always plus for the last. For the last, you're going to get 1 squared, which is just 1. Okay. Are we okay here? Now we can cancel, which is what we're hoping for on these types of problems. So we got the limit as x approaches 1 of x squared plus x plus 1. And I'm just plugging 1 into that. So I've got 1 squared plus 1 plus 1. And that's going to be 3. Oh, what did I forget to do on this problem at the very beginning? It doesn't change my answer. But what was I supposed to do at the beginning of this problem? So I was supposed to do direct substitution. I was supposed to try to do 1 cubed minus 1 over 1 minus 1. But that would give me 0 over 0. So mentally, at least, you're supposed to be doing that every time. As you can see, I've already, on example 5, went to the assumption that I'm going to get 0 over 0. And I am the teacher that should know to check for this every time, right? Because if you don't do that, there will be some that are direct substitution that pop up that are hidden in amongst the hard problems that are going to get you. So try to remember to do that every time. All right, so that is one type of problem that we are going to see where we can factor and cancel. So we've looked at direct substitution, we've looked at factoring and canceling. Let's do a quick review of how to rationalize a root, and then we're going to talk about rationalization. So when you were in pre-cal, I actually did a better job of going over this than I have in the past because they kind of added it to our curriculum. We had to rationalize expressions. Here's the good news for you. In AP Calculus, you do not have to rationalize your answers. So if you get 1 over the square root of 5, you can leave it 1 over the square root of 5. You do not have to rationalize answers. In fact, on the free response questions, I would not rationalize, because if you do rationalize and you mess up, they're counting whatever you messed up as your answer, and you will lose points, even though you had it right if you had just left it. So don't rationalize on free response. Now, you will see sometimes maybe you get 1 over square root of 5 and it's a multiple choice question. 1 over square root of 5 may not be there as an answer. You might have to rationalize to get that correct answer there. So you still have to know how to do it, but you don't have to rationalize whenever you're working out problems that are not multiple choice. So, remind me, rationalization is that we can't have square roots in the denominator. So, how do I get rid of that square root in the denominator? Okay, we're going to multiply. On the top and the bottom, what are we multiplying by? Square root of 5. And if we do that, we will get square root of 5 over square root of 5 times square root of 5 is going to just be 5, right? You can think of it a couple ways. It's either square root of 5 squared, in which case you get 5, or you could think of it as square root of 25, which is also 5. When you multiply square root by itself, you get just that number, right? And so this would be your answer rationalized. Okay? It's different whenever we have an expression like 2 plus the square root of 6 in the denominator here. Anybody remember how to get rid of that? How we can get rid of the square root in the denominator there? What do we do, Bo? Yes, so on the top and bottom, what would we be multiplying for this one, Bo? 2 minus square root of 6. And I'm going to put parentheses around this as well. Anybody remember the name for that? What do we call it? What was it? I don't know if I use the word complex, although I think that's okay. Actually, complex, I think, has to have an I with it. So there are probably times that you did use complex conjugates because you had I's. Since this doesn't have an I, we would just call it the conjugate. Okay, so that's just a fancy word. I'm going to try to sprinkle in fancy words here and there because you guys are going to college next year somewhere. I'm pretty sure everybody is going to college somewhere, are the current plans. Hopefully you're not going to, veer off from those. Unlikely that you're going to have one of these professors if you go to Surrey. But if you go to a big college anywhere, there is a decent chance that you may find yourself in a math class taught by a grad student who is getting their PhD, or, well, either way, either a grad student from a foreign country that is getting their PhD in math, or somebody else who already has their PhD in math, who may or may not be from a foreign country, but math professors a lot of times, big colleges, a lot of them are from foreign countries, which is great and makes them very interesting people, but sometimes their accents can cause a problem for you understanding. And not only accents, but like their whole mindset about things. I know my husband had a professor for differential equations that only just like derived formulas the whole time. Like instead of just doing the problems, he showed you like these extensive proofs of why you could multiply by the conjugate and all of this. And so it was like a whole different mindset sort of thing, like way above here. So I tried to throw in fancy words like conjugate so that when you go to college, if you get one of these professors that is kind of a level above, Khan Academy is guilty of this sometimes. Khan Academy, which I mean is good. They're using very precise language. But Khan Academy, sometimes my students watch it and do not know what they're talking about because they are using lots of fancy language. So I try to use it some, but you will find, as I said, my notes, they're like the redneck version of Khan Academy. Not only in my accent, but also sometimes I just, use not so precise language. I try to work that in so that when you go off, you will know what we're talking about. You'll know what they are talking about there because it will really help you. So conjugate is a fancy word that we want to know there. So when we multiply by the conjugate, in the numerator, you got 8 times 2 minus square root of 6. You can distribute that if you want, or you could leave it factored out. It really does not matter. In the denominator, though, we want to distribute here. So 2 times 2 would give us 4. And then I'm going to write it this time just to show you, but I usually do this part in my head. 2 times square root of 6 gives us 2 root 6. And actually, negative 2 root 6 there. And then 2 times square root of 6 here is going to give us positive 2 root 6. And then at the end, we'll have negative 6. And so what happens here is those middle terms are going to cancel out. So you'll probably find yourself just skipping that, writing that middle part there. So we've got 8 times 2 minus square root of 6 over 4 minus 6. Which is going to give us negative 2. And on this particular one, it would be helpful to keep it factored out like this, because that 8 and that negative 2, they can reduce. You could make this a 4 and that a negative 1. So you've got 4 times 2 minus square root of 6. Over negative 1, which would probably be written as negative 4, 2 minus square root of 6, or negative 8 plus the square root of 6. There. Okay. Again, if you get an answer like this, don't rationalize it. Leave it 8 over 2 plus square root of 6. That's fine. But we need to know how to do this for the next step that we're doing.
At the end, don't you try to get everything out of the square root?
If you possibly can, you want to, but in this case, you're not going to be able to get rid of that square root of 6 without going decimals and getting an approximation, because you can't break down square root of 6 with anything, and we can't multiply by the conjugate again unless we also do it on top and bottom, and what that's going to do is just take us right back to what we had over here.
Wasn't there something we did where you would make it like 2 plus 4, and take the square root of that 4 and take it out, and you get 2 square root of 2?
Yes, but 6 will not break down. Because, like, if I had square root of 24, then I would break that down. And I would do, that is 4 times 6, so that would be 2 times the square root of 6. But for 6, the only thing you could break it into is 6 and 1, which would do no good, or 2 and 3. Can you take the square root of 2? Can you take the square root of 3? No. So 6 will not break down any further, so you'll leave it. But if it were a number that would break down further, you would break it down further. Okay, now my main reason for wanting to review this is because we were going to use a similar tactic whenever we deal with limits. Okay, so if we look at example 8, we've got square root of x plus 1 minus 1 over x. So first step we always need to do is plug in our number, 0 plus 1 minus 1 over 0. And that's going to give us square root of 1 minus 1 over 0. What is square root of 1? It is 1. Don't forget it. Every year. Almost every year. I can't say for certain because my memory is bad. But this is often. I have students in calculus who do a whole problem and they leave square root of 1 in the whole problem because they have forgotten that the square root of 1 is 1. So watch out for it. It'll get you sometime because we just every once in a while have like a brain lapse there. But we're getting 0 over 0 here. That tells us we need to try something else. So if you're seeing square roots, there is a chance that rationalizing may help you. Now, in this case, our square root's not in the denominator, it's in the numerator. But just moving that square root to the other side may help us cancel something. So we are actually going to rationalize the numerator in this case. So I've got the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. And I want to multiply by the conjugate here in top and bottom. So the conjugate of this, the square root of x plus 1 stays the same. Don't change that sign there. The only sign that changes is this sign right here in between the square root and your number. So it's going to be square root of x plus 1 plus 1. We've got to multiply on the top, and we've also got to multiply on the bottom. So if we do that, we're not losing our limit notation yet. We're holding on to it even though it's annoying and we'd like to shortcut it away. What do I get when I multiply square root of x plus 1 times square root of x plus 1? Just x plus 1. And then I'm not going to write it this time. When I multiply the outside, I'll get positive 1 square root of x plus 1. When I multiply the inside, I'll get negative 1 square root of x plus 1. As long as you've done your conjugate correctly, that should happen every time. Those middle terms cancel out. And then so I've just got to multiply negative 1 times positive 1, which gives me negative 1. In the denominator, don't multiply those together. Because we want something to cancel, and it's going to cancel more easily if it's factored. So I've got x times square root of x plus 1 plus 1 in the denominator. So we should see some stuff happening. What's going to happen with that plus 1 minus 1 right there? Those cancel, correct? So that's just going to give us x over x times square root of x plus 1 plus 1. And then what's going to happen? The x's cancel right here. Make sure that you keep that expression in the denominator. What do we put in the top? There's nothing left, so what should we put there? We're going to put just a 1. It's like, that's a 1x, so that 1 stays in the numerator. So now we're down to limit as x approaches 0 of 1 over square root of x plus 1 plus 1. And once you have canceled a value that has x's in it, it should, in most cases, now be okay to plug that number in. So now we're going to do direct substitution. It is at this point that we drop our limit notation. So we're going to have 1 over the square root of 0 plus 1 plus 1, which is 1 over square root of 1 plus 1, and that's just going to give us 1/2. That'll be our answer here. Okay, questions on that one? All right. Okay, let's look at. What did I say? Hold on. Let me look at tomorrow's notes to remind myself of what we're looking at tomorrow. There have been times I did this all in one day. I'm not sure if I squeeze theorem and oh yeah, trig. Yeah, we need to do them all day. Okay. Okay. All right. So here's another thing you're going to run into. You might see factoring and canceling. Well, direct substitution, factoring and canceling. Something that needs to be rationalized is usually going to have a root in it. Then everyone's favorite, complex fractions. Fractions inside of fractions. So every time, first thing, we're supposed to do direct substitution. So we'd have 1 over 0 plus 2 minus 1/2 over 0. That is going to give us 1/2 minus 1/2 over 0, 0 over 0. Again, you don't have to write it down, but you need to think about it each time because there's a chance they've thrown in one that actually works with direct substitution, even though it looks crazy like this. But that does not work. So, if we see complex fractions, we, in general, want to get rid of the complex fraction. So there are two ways of thinking of doing this problem, and I'm going to show you both of them. The one that I prefer is to multiply through by a common denominator on top and bottom. Okay? So over here, the denominator here is just 1, right? So if I look at my denominators here, I've got x plus 2, 2, and the 1. Right? What would the common denominator be? Least common denominator. What would it be for those? What? X plus 2 is part of it. It also has to have a 2 with it. Okay? So I need the denominators of these to be x plus 2 times x plus 2. So there's a couple ways you can think about doing this. So we could just multiply everything on top and everything on bottom by 2 times x plus 2. So if I do that, I've got 2 times x plus 2. And then over here, I've got 2 times x plus 2. And right here, I'm multiplying by 2 times x plus 2. All right. So for that first term, x plus 2 would cancel. For the second term, I got a 2 on top and bottom that will cancel. Will anything cancel for the second one, for the denominator here? It will not. So that is going to give us the limit as x approaches 0 of, here we'll have just a 2 because the denominator canceled, right? And then here we will have x plus 2. And then in the denominator, I've got x times 2 times x plus 2. So I could write that as 2x times x plus 2. Now I messed up. What did I do wrong? I messed up on purpose to see if you guys could see what I did wrong. I really did this time. I say that sometimes, but I really did. I've made a mistake. It's not in my multiplying. It's a really simple mistake that I have. What do you think, Raven? I need parentheses around this x plus 2 because I am subtracting that entire thing. So that means that I should have the limit as x approaches 0 of 2 minus x minus 2 if I distribute that there. So be really careful if you got a minus sign. You've got to distribute it. Okay. What is 2 minus x minus 2? That's going to give you negative x because this positive 2 and this negative 2 right here are going to cancel each other out. So now I'm looking at limit as x approaches 0 of negative x over 2x times x plus 2. What can happen now? Okay, this x right here can cancel with this x right here because I've got multiplication right there between. So what's that leave me with in the numerator? A negative 1. So I got limit as x approaches 0. And then I've got 2 times x plus 2. And so once that a term with an x in it cancels, you can probably do direct substitution. So that would be negative 1 over 2 times 0 plus 2, which is going to be negative 1 over 2 times 2, which will give us negative 1/4 as our answer. that is one option that you can do this. The other way I'm going to show you is still really the same, but you're just thinking of it a little bit differently. So what we could do instead, so I'm gonna write this down, but you know this is done. We could just do it the way I just did it. I've got 1 over x plus 2 minus 1 over 2 over x. We might choose just to deal with the numerator first and get common denominators there. So I could do that by multiplying this by 2 and this by x plus 2. Like so. So I'm only getting common denominators in that numerator part. So that would look like this. I would have 2 minus x plus 2. And because I have common denominators, both of these are 2 times x plus 2, I could write it like that. But it would still be over x here. So I've got a fraction over, I could make that a fraction right there. What can I do when I've got a fraction over a fraction? Dividing fractions, easy as pie, flip second and multiply. So I could do it this way, limit as x approaches 0 of, I'm going to distribute that negative right there, 2 minus x minus 2 over 2 times x plus 2 times 1 over x. That is the limit as x approaches 0 of negative x over 2 times x plus 2 times 1 over x. These x's right here can cancel, and you'll see from this point we've got limit as x approaches 0 of negative 1 over 2 times x plus 2. And that is the same thing we had over here, and it just finishes up that same way. All right, just a different way of doing the same problem. So either one is fine there. Okay, and I've got one more that we're going to look at. Oh, this one looks bad, doesn't it? All right, so our book uses this notation quite a bit where we have delta x. And when we get to limit definition of derivative, you'll see why that we use it. So, first of all, delta x is a single variable, right? So when we see it, it is not delta times x. It is a single variable, delta x, that go together. All right, so if we try direct substitution here, we're only plugging in 0 for the delta x, not the x, just the delta x. So it's 2 times x plus 0 squared minus 2x squared all over 0. And x plus 0 is just x, so this is going to be 2x squared minus 2x squared over 0, and what are we going to get? 0 over 0 right there. So, indeterminate form, it's not our answer, it means we got to keep going. So, what we want to do here is kind of, well, not really the opposite, because we're going to do sort of the same thing here. It would be nice if we could factor and cancel, but we can't factor and cancel with this whenever we have this x plus delta x squared, right? We can't factor that. So, we're actually going to expand first. So, we're going to do the limit as delta x approaches 0 of 2 times, and we did this a lot in pre-cal, we can square, double, square, right? So x, we're going to square it. We're going to multiply x times delta x together, which is just x delta x, and double it. So we'll have a 2x delta x. And then we square the last, so we'll get delta x squared. And don't forget that minus 2x squared there. If you need to, over to the side, you can do x plus delta x times x plus delta x. Think of that delta x like a y. if it was x plus y times x plus y. All right, that notation's a little scary, but it's just like a separate variable. We need to distribute that too, so we'll get the limit as delta x approaches 0 of 2x squared plus 4x delta x plus 2 delta x squared minus 2x squared all over delta x. Do you guys see anything that will cancel? Okay, 2x squared, negative 2x squared. Those will cancel. And so let's think about what that leaves us. It leaves us 4x delta x plus 2 delta x squared. Is there anything I could factor out of that? A delta x. I can take a delta x out. So I'm going to do limit as delta x approaches 0 of delta x times. So I'm taking away a delta x. That's going to leave a 4x plus 2 delta x, because since that's delta x squared, there's 2 of them, we're only taking one of those out, over delta x. What can happen now? Those delta x's can cancel, and when those delta x's cancel, now we're just doing the limit as delta x approaches 0, the 4x plus 2 delta x. And we're going to plug in 0. What are we plugging in 0 for? Delta x, not x, just delta x. So I will get 4x plus 2 times 0. So this looks a little weird. What's our answer? 4x. So in problems like this, not always, but sometimes you will get x's in your answer. Actually, not always, but a lot of times. Let's say you'll get x's in your answer. So everybody go home, show your parents this problem. They'll be impressed. I think everybody's parent. Anybody got Connor's parents might not be that impressed. But everybody else's parents will probably be impressed, I think, because it looks scary when you throw that delta x in there. So these are some types of problems you'll see as well. So the assignment tonight comes from the textbook. It looks like a lot, and it might be a little bit a lot, but 5 through 17, those should be direct substitution. Those should be really fast. Okay. So 5 through 17 should be direct substitution. 51 through 66, these are the problems where you're actually going to have to do some different strategies. Although, watch out, they may have put some direct substitution in that section as well. That will be your homework. Go ahead and get started. You got about 10 minutes. Maybe you can get through those first few right now.